So hello, I am Mihai, like Taylor Swift. It's Mihai, I am the speaker. And I will talk about secure packaging for AI/ML models. And you will hear a lot of AI in this talk. And it's kind of like AI everywhere. So sometimes I will use ML instead of AI. They are not exactly the same, so ML is like a subset of AI. But just to not bother you by just repeating AI every time, I will use them interchangeable. And I will also talk about software that is not AI-based. And in order to give it a name that we can refer to, I will call that traditional software. So traditional software is software that doesn't use AI. The rest is AI or ML software. And these two types of software have stuff in common and stuff outside that is not common. And today, we are going to focus on the common parts. And what we mean by the common parts, one of them is about history of how these types of software have been developed. They started first as just research or hobbyist, like for traditional software, just writing assembly for games and so on. Then later, they become used in industry, like traditional software. You started having software being built by IBM and so on for universities, and etc. The same for AI, ML. You started having it built like Google Translate and so on. And then after that, it became commodized, and people started using it by themselves. And you got the spread of open source, and everyone can build their own software and so on. And we see the same thing for ML. Since around last year, when LLMs started exploding, we now have an explosion of AI-powered applications. So the two timelines are similar. They are just on different timescales. So I couldn't use like a logarithmic scale or something like that to represent both in parallel, but imagine they are there. There is another thing in common that matches this timeline. We have hackers, attacks, cybersecurity incidents, and so on. For traditional software, we all know about all of these problems. It's not recent. For ML, they are also happening recently. So we have researchers, academics writing papers about AI and ML. We have GPT-4chan. Some years ago, there was a bot that got released and was learning from Twitter, and then Microsoft had to take it out because it started spreading nonsense. We also have more recent articles, the poisoning of ChatGPT, and even a model that was deployed on Hugging Face to spread fake news, and it was called like, this is a GPT model, and you can use it, and actually it was a poisoned one. So we have to handle security for AI. And this is more relevant because right now, AI is used also to build software that is not using AI in the future. So GitHub Copilot or other similar AI-powered applications. There is even Demo GPT that allows you to write code without actually writing code. You just tell Demo GPT, I want an application that does this and that and that, and behind the scenes, it writes the code for you. And this is not only for GPT. We just saw a presentation where machine learning neural networks have been used for dependency management. So what is the problem? If the ML model gets attacked, gets injected with malware, then the dependencies could be altered, or the entire supply chain would get attacked. So we need to look at the intersection between AI and security. And at this intersection, we actually have three possibilities to fill in this gap. We have security from AI, where we basically try to protect people from damage that is created by LLMs or other similar AI tools. We're not going to cover this today. We also have security via AI. There is going to be a talk after mine about using LLMs to power the supply, to secure the supply chain. Or we could use LLMs to give us fuzz harnesses for OSS fuzz. Also another cover of this talk. And finally, there is security for AI, where we want to bring security to the field of developing AI. And this is the focus of this talk. And because this is a PackagingCon conference, we are going to focus only on the supply chain involved in here. And why is this relevant? A recent news piece around a month ago or 2 months ago said that 38 terabytes of data were exposed in a Microsoft bucket, in a cloud bucket from Microsoft. And besides the data that was there, there are also a lot of models. And several of these models were actually in pickle format, so somebody could just load them, modify the pickle file, save the new thing, and then serve the models. So now when somebody wants to deploy those models in production, you load the pickle. Loading pickles is totally unsafe. You get owned. And even if the model is not in a pickle format, the most powerful machine learning frameworks, TensorFlow, PyTorch, both of them are actually Turing complete. So the model that you develop is like a specific language that you write, and the entire ML is like written in a domain-specific language inside it. So it's very dangerous to allow users to modify models outside of the normal channels. Even worse, let's consider the case of Kaggle. Kaggle is a hub where you can both run notebooks to develop machine learning solutions to solve some competitions, but it is also a hub for models. You can train your model, you deploy it on Kaggle, and somebody else might use it later. So somebody malicious that wants to win all of the Kaggle competitions in the future might deploy a very useful model, very useful, that is malicious, and then wait for people participating in future competitions to load that model and then own them. So somebody malicious, let's say one evil model and maybe a GPT model, because everyone wants to use GPT now. And I'm uploading, the malicious user is going to upload this model to Kaggle. In the model card, they are going to give very helpful descriptions, so basically tricking people to use the models. And in case people look at the model name, we can also change the name. So instead of evil model, maybe it's nice model, and GPT-4 friend. It's the very friendly bot that comes to your neighborhood. So the reason is, on their own, the model are not attributable to the user that uploaded them. So if you have a model, you don't know who created this, what is inside. Models are very inscrutable. For a binary, at least, you can run some tools to find out, like you can disassemble them. You can understand what is happening in there. For LLMs, all you have is just a bunch of numbers and some architecture. It's very hard, once you get these two pieces, to put them together and understand what is happening, especially for big models. So the conclusion is we should protect the ML supply chain. And in order to do that, first, we have to understand what it is. So the general ML model pipeline has 3 phases. The first phase is researchers looking at the data, preparing it, creating some models, experimenting with that, and looping around until they have something successful. Then the next phase is publishing this model such that it can get later used in production. So these are the 3 stages. And let's focus on the data preparation to model publishing, because that's the part that actually is the supply chain. So let's say I am an ML developer, and I want to build a successful ML model for something. So I have a database, a data set that I want to train from. So in this example, for example, I picked CIFAR10, which is a set of images that are labeled in 10 different classes, like cars, clothes, and so on. I also had to pick an ML framework in which I can train my model. So here I picked TensorFlow, but you can pick PyTorch if you want, doesn't matter. And I load the data from the database. Of course, behind the scenes, this downloads the data from the internet, downloads it locally, reads it, and so on. OK, so let's say I have the database. I already have my code to train the model. I actually have to write that code. So I say I'm building a sequential model that has several layers in there. It's not relevant exactly what the layers are. It's just an example. So right now, me as an ML developer, I have the model source that I just wrote. I have a data set that I downloaded from the internet, and I have a framework with maybe other dependencies. So if this data set is using images, I probably need a dependency library that can parse images and return back the pixels. So I have everything together. The next step is combine everything together and train a model. OK, now that I have trained this model, I have to deploy it somewhere such that it can be used. So let's say I upload it to Kaggle, or I upload it to TF Hub. And now somebody else would download my model and start using it in production, so for inference or for winning a new Kaggle competition. And if we look at this diagram and we squint a little, we realize that we have seen this several times, this conference. It's basically the salsa diagram, the diagram for the typical ML, for the traditional software development. So this is the traditional software development. This is the ML diagram. The only thing that changes are the labels, but they are exactly the same. You have some source, you have some dependencies, combine them together in a build, you deploy an artifact that then gets used. So why not think of a possible future where you can just say, CMake my model, or Bazel build my model, or something like that. OK, so let's also look at possibilities for attack. You have seen several times the salsa diagram with the attacks labeled ABC to age. Instead of labeling them, I just selected a few of them for each of the blocks. If I look back at the ML diagram, it will look the same. I went too far. So I can still compromise the place where I store the model, or the model itself. Somebody could still compromise the training process, could still inject vulnerabilities in the dependencies, or poison the dataset, or could compromise the source control for the model, where I'm training it and sharing it with others. So it's exactly the same avenues of attack as for traditional software. So now let's think about how we are going to secure the supply chain. In traditional software, the first thing we try to secure is tampering after the build. So let's try to protect this part. So let's say the model has been already trained, has been deployed to the model hub, and now we want to prevent tampering here. We have a solution in traditional software, and that is called Sigstore. And we can use that here too. So basically what we do with Sigstore, let's say I am the model trainer. Let's see if the laser works. Here in the middle, after I train the model, when I try to upload it, I start the Sigstore signing flow. So this creates this first starts an OIDC workflow to send an workload identity token to the Sigstore CA, from which I get a certificate. Then also behind the scene, this certificate is used to sign the model. The signature event is stored in the Sigstore transparency log, and I get back a proof that my model has been signed and is included at this position in the log. Finally, once I have the signature and the model, I can upload everything to the model hub, both the model and the signature. And the model hub, upon upload, can verify that, yes, this is a model that has been signed, the signature is valid, store everything together. Later, when somebody wants to use the model, they could also verify the signature. Another advantage of Sigstore is that because it's a transparency log, if I am suspicious that somebody uploaded a model in my name, I can look through the transparency log and find out all of the models that are signed under my name, under my identity. If I detect something that doesn't match, I can signal that that's not me. Or the other way, if I suspect that a model is actually not trained by the person that they say it is, I can try to see if it is in the signature is in the transparency log or not. So again, signing is not the full image of the story. It is not the full part of the story. You also have to verify the signatures. So we have tried to sign several LLMs, several models. And both signing and verifying times are very small, even going from models from 8 kilobytes all the way to 14 gigabytes. So this is the part about verifying the models after they have been trained. But the other part of securing the supply chain is trying to prevent tampering, including during the build. So let's try to protect everything, except submitting bad codes or using a vulnerable dependency. That we cannot really protect, so I extracted them out. I also extracted the databases. Oh, I already gave the hint. We are going to use Salsa. I also extracted the databases as a separate thing because it's a little bit unclear how we are going to record a data set in the provenance for Salsa. Like, do we record that this is the CIFAR10 data set, or do we record every element, every image in the data set, and we hash everything? Each one of them has some benefits. Like, if you record only the name, it's fast. If you record every row, it's lower, but then if somebody just changes 1 pixel in the data set and says, now this is the new CIFAR10, you'll notice. So it's still something in progress that we'll have to decide, that we'll have to work on. But so far, let's just focus on the part without the databases. So we want to train a model and generate Salsa provenance. And you know there are several levels for Salsa, level 1, level 2, level 3, that provide different guarantees. We are going to actually use the GitHub generator for Salsa. and train a model inside GitHub Actions. And at the end of this, we'll get both the model trained and the provenance. This is a demo that this can be done. We are also looking at using, for example, tecton chains to train models in longer training pipelines, because, for example, on GitHub Actions, you cannot run something for more than 6 hours. And if you have a large number of repositories in your organization, each action is taking the time from the other ones, so you have a specific pool for the entire organization. So we are looking at other ways in which you can train models and get salsa provenance on top of that. We currently support 6 different model formats, 3 for TensorFlow, 3 for PyTorch, but the repository is open for further pull requests to support other types of models and so on. If you look at the TensorFlow models, you would notice that it contains the most recent format for Keras or the legacy HDF5 formats. It doesn't contain the saved model format, which is a directory. This is because there is an issue with salsa verifying multiple files at once in the provenance. I could interchange the name of the 2 files, and the signature, verifying the provenance will still say, yeah, everything is valid, all of the hashes match. But for a model, if I rename the 2 files, now I have a totally different thing. It's no longer the same model. So we need a way for salsa to say this entire directory in itself represents a single unit. And this is an extension that we'll have to do to salsa, but it's doable. OK, so for future, on the part of the model signing, we will still work on the hash performance and making it scale to even larger language models. We are already working to integrate this with ML framework. So when you say model.save, behind the scene, it will also start the signing workflow. So you don't have to sign the model and then separately run another command to sign it. And also, when you load the model, you can specify verify signatures equals true, and it will verify the signature before loading it. And this way, if a model uses a pickle format, you verify the signature. If it was maliciously altered, the signature would fail, and you won't be owned. And we are also talking with Keras and other model hubs to integrate signatures into model cards. So you would go to Keras, you will see, oh, this is a nice model that I might want to use. Oh, in the model cards there it says it is signed with Sigstore. If there is a button, I can verify the signature. I can use this model. I have more trust in it. On the Salsa for ML part, we are, as I said, we are looking to scale outside of GitHub Actions. So for example, looking with tecton chains and other workflows. We are also looking to expand support to saved model for TensorFlow. And the recording dataset provenances, which is the problem that we don't know exactly. Do we want to do the fast thing or the thing that prevents as much manipulation as possible? And finally, we want to meet the ML researchers on the platform that they use. So if people use Jupyter Notebook, we want to make Jupyter Notebook generate salsa provenance at the end, if that is possible. It's something that we'll have to explore and see. And I also put 2 more items with question marks. Maybe we also want S-bombs for ML. Maybe we want vulnerability information for ML, and so on. That is something to be discussed in the future. What we can say right now, so from the entirety of this talk, if you remember this slide that is perfect, is that we can protect the ML supply chain using exactly the same tools as the traditional software. We don't need something different. We don't need a separate salsa track. We don't need a separate way to sign models. It's just a different way to record the hash of an entire directory, or a different way to record dataset dependencies, but everything could still be incorporated in salsa. And on this slide, I have 4 QR codes for different things. First is the repository, where we have the model signing and the salsa GitHub generator for ML training. Then there is a blog post on the Google security blog about the same repository and with a little bit more details about the entire story. The third QR code is about a working group under OpenSSF for AI and ML. It's currently meeting every Wednesday. I forgot exactly the time, but the QR code links to the Slack channel, and I can give you the meeting code there and so on. And finally, the last one is linking to a Google post about the secure AI framework that Google released this year, which is basically trying to bring security to AI. And the first principle of SAIF is that we want to expand the security foundations that we have developed in the past to the AI ecosystem. And basically, this entire work is part of that. And with this, I'm opening the floor to questions.
Thank you, Mihai. Are there any questions?
Knowing nothing about the saved model format, can the format itself sort of provide a canonicalization or sort of stable format that could be hashed as like a single entity? Or is it just like a directory listing?
That is the reason why there is now the Keras format, which basically takes the folders and the directories from the save model and meshes them together into a JSON plus adjacent data at the end binary. But a lot of the models that have been trained so far with TensorFlow are using the save model format.
Gotcha.
Any more questions? None?
Thank you.